Hello, everyone. Okay, so let's resume where we left off. So let's cross this out because I rewrote it. Yeah, so I think I wrote that there. Well, anyway, let's keep going here. Okay, so one thing we want to take note here is that for every electron in the non-asterisk, those are called electrons. In bonding orbitals. So we count them. We're going to count all the electrons that don't have an asterisk. 2, 4, 6, 8, 10. So that's 10 electrons. And then if we have electrons in antibonding, we have 2, 4, 5, 6. So 6 electrons. So you see here we have a difference of 4 electrons. 4 more electrons are in bonding molecular orbitals. So that's why an oxygen molecule is predicted to have a bond between the two oxygen atoms. It's considered to be a molecule. And that's because we have more bonding electrons than antibonding electrons in those orbitals. Okay, so that's how we determine if a molecule is predicted to exist or maybe not exist. All right. So these the MO diagram I just drawn, this best describes oxygen, very electronegative atoms, and that's because the sigma 2p is usually lowest in energy. So the sigma 2p here is usually lowest in energy when you have electronegative elements. When you're considering the bonding between two electronegative elements, such as oxygen and fluorine. So it describes the bonding the best for oxygen and fluorine molecule. Okay, so however, in some molecules, there's a modified MO diagram that's used to better describe these molecules. And that's because the interaction between the 2s orbital, so the 2s orbital interacts with the 2pz orbital on the other, and this causes a change in the energy levels of the molecular orbitals that we saw before. So you see here, so when we have so typically speaking, so when we get to, if we look at this graph here, we look at this situation here. So you see here, this is the sigma 2pz, and then see how it interacts. It interacts very closely with the 2s on the elements. So usually the more electronegative we go, so the further we go across the periodic table, this orbital is going to interact more favorably with the sigma 2s orbital. So in this case, this one will interact with the 2s more effectively here. So if we look at these orbitals here, the interaction between the 2 pi the sigma pz right here, it interacts with the s orbital. So we see here those energy levels are getting closer together as we move towards the right, and that causes the orbital energies here to flip. So in molecules like beryllium, boron, carbon, and nitrogen, this orbital is actually higher than the pi 2px and 2py. But in molecules like oxygen, fluorine, that level, as we see here, is below it. So it kind of gets these energies change based on the molecule we're talking about. Okay? All right. So here's the MO diagram that we use to describe less electronegative elements such as boron, carbon, and nitrogen. So let's do an example Um, let's see here. Did I want to go over an example here? So I was going to use an example. Let's do carbon's example. So if we were to fill up the, let's do nitrogen actually. So 2 nitrogen atoms. So nitrogen has 7 valence electrons. So we should have 14 electrons each. So they have a fill the 1s orbital. So let's just do this example for nitrogen. And then nitrogen has 3 unpaired electrons here. So you see here, the energy levels of the 2p and these pi bonding orbitals, they're switched compared to O2 case. You see? So that has to do with the electronegativity of the oxygen atom. You see here? So there's no anti-bonding orbitals that are populated in the pi star or the sigma 2p star. So this molecule is predicted to exist, and nitrogen is a very stable molecule. It makes most of our atmosphere. Okay? All right. So now that we've been working with bond order, let's talk about another topic related to that, and that's called bond order. So bond order, it's a number that indicates the number of bonds between a pair of atoms. That's called a bond order. So we can calculate it from Lewis structures. For example, oxygen has a bond order of 2 because of the double bond. So double bond here. So our bond order equals 2. Okay. When we have resonance structures to describe a molecule, so the bond order is determined by an average of these structures. So in this case, the bond order for sulfur dioxide is 1.5. So we could say in each structure, there's an SO single bond, or the SO bond can either be a single or double bond. So we take the average of those two. We have 1 single bond and a double bond. We have 2 structures that describe these bonds. Divide by 2, and we get 1.5. Okay? All right, let's go on. So MO Dewey, there's another way we can calculate bond order. Okay? All right. So we calculate bond orders by assuming that 2 electrons in a bonding molecular orbital contribute 1 net bond, and that 2 electrons in an anti-bonding orbital cancel the effect of 1 bond. So bonding orbital, you form 1 bond. You form an anti-bonding orbital, it negates the effect of that 1 bond. So you're back to 0 bonds. Okay. So let's try and calculate the bond order in O2. So there are 10 electrons in bonding molecular orbitals, and 6 electrons in the anti-bonding molecular orbitals. If we look at the electron configuration we wrote right here. Okay, I noted that down right there for us. Okay, so to calculate bond order, we take the number of bonding electrons, and we subtract that from the number of antibonding. Sorry for the lack of space there. And we divide this whole number by 2. So we have 10 minus 6 over 2. So that gives us a bond order of 2. Okay? All right. So if we look at the Lewis structure of oxygen and compare it to the molecular orbital model of oxygen, they both yield the same bond order, right? We get 2, a double bond. However, if we compare the structures, the Lewis structure has all the bonds paired, right? And see, all the bonds are paired, so all electrons here are paired. But if we look at the molecular orbital model that we drew previously, we see here those are all paired. But oh, look at these two electrons. These two electrons are not paired. So why is that? So some are paired, but these are not paired in the molecular orbital. So why is that? Why do we have that discrepancy? Okay. So what's the deal here? What's the deal? What's the deal here, right? So what's going on, right? So we can test the prediction. So the Lewis structure predicts oxygen doesn't have any paramagnetism, so it shouldn't interact with a magnetic field if all the electrons are paired, right? So we can test the prediction of both of these models by studying the effect of a magnetic field on oxygen, okay? So recall that atoms or molecules in which the electrons are paired, we call them diamagnetic, so they won't interact with a magnetic field. So this should say repelled. By both poles of a magnet. So those that have one or more unpaired electrons are paramagnetic, and they'll have the ability to interact or be attracted to a magnetic field. So we can do a little experiment here. We liquefy oxygen. So it's really hard to see, but this is oxygen at a very, very low temperature. And you see here, in this magnet here, we can see the oxygen atom get between those two the poles of this very strong horseshoe magnet. So this is direct evidence that it's being attracted to the poles of this magnet and not being repelled. If it was being repelled, it wouldn't stay near these poles. So the fact that oxygen can be stuck between this gap, it will bridge this gap between the poles of a horseshoe magnet, So this could have important implications for imagine you could make a material that a bridge that's held up by magnetism instead of traditional nuts and bolts or like planks and stuff. So I don't know if that's something in the near future or not, but it's interesting what chemistry the implications you can get out of these findings. So this one is definitely an interesting one. So liquid oxygen is so strongly attracted to the magnet that it can bridge the gap here. And so essentially, if you have a magnetic material, you can also do that same thing. It doesn't have to be liquid oxygen. It won't work because liquid oxygen is a liquid, and as soon as you bring it to room temperature, it will just vaporize. And that's not a good thing if you rapidly vaporize something. But this could be applied to other things as well. So, in conclusion, since we can say oxygen is clearly magnetic, the MO model is superior to our valence bond model, which could not explain the paramagnetism of oxygen. Okay, so thus we can now represent the best Lewis structure for oxygen, which is this structure, where this we say that these, if we drew it a little bit differently, we can say something like, we can say that this lone pair is sharing electron density with this unpaired electron to make it stable. So those are some interaction lines here. So we can call them a electron interaction here, where the electrons are being shared between this lone pair and this unpaired electron. So this is the unpaired. This is the best Lewis structure based on our data and our model. But in valence bond theory, this is not a great Lewis structure, and that's because both atoms don't formally have an octet. But this is the structure we would draw for oxygen. So this is called ground state oxygen. So like I have mentioned or referenced before in the past, so this is what we call triplet oxygen. And the oxygen I have been drawing, so this oxygen here is singlet oxygen. Singlet state, or what we call the oxygen's first excited state. So this form of oxygen is used to do chemical reactions, and it's not the most stable form of oxygen. As you can see why, the double bond there is not really strong. It's actually quite reactive and can react with a bunch of organic compounds, and those are things we won't talk about here. Okay? So that's how we would describe the advantages of MO theory is that it can predict the structure, it can predict the structure a little bit better than valence bond theory. So that's why they're kind of taught and they prevail. They are the current models of chemical bonding to our understanding, and the role of molecular orbital theory is used in computations to do chemical calculations. So in chemical calculations, we find the molecular orbitals for atoms and molecules, and we use that to calculate energies, and we can get valuable information from these calculations using computers, and it can help guide a more intelligent way to do science rather than trying to use our best guess on intuition or our understanding on first basis chemical principles. So MO theory is definitely a powerful technique that we have to aid us in our adventures and discoveries in chemistry. Okay, so let's go over the last example here. We're going to say use the molecular orbital diagram in this below to calculate the bond order in nitrogen oxide. Okay, so we're going to compare the results of this calculation with the bond order obtained from the Lewis structure. Excuse me. Okay, so first let's calculate the bond order. Okay, so if we look at both of these structures, right, they both have a double bond, so the bond order is 2. Okay, so it's both 2. So we have 2 structures here. In this case, this will be negatively charged, and oxygen has a positive charge. So nothing wrong about that. Okay. So if we look at both of these molecules, we should have 5 plus 6 valence electrons, 11, so an odd number. So we're going to have a radical species. And we see here that in our structures, we have 2, 4, 6, 8, 10, 11 electrons in both structures. All right. So let's now look at an example. Okay. All right. So now let's fill up these orbitals here. So nitrogen has, oh, oops, I should have changed this. So you simply can't copy and paste. So, all right, so nitrogen has 7 electrons, right? And oxygen has 8, so we should have a total of 15 electrons. All right, so let's fill them up. 1, 2, 3, 4. Fill our diagram here. Okay, so nitrogen will have 3 p electrons, while oxygen will have 4. All right, so let's fill these up. 1, 2, so a total of 7 electrons. Okay, so now let's count up the bond order. So let's count up the electrons here. So for bonding electrons, so for bonding, we're going to have, so let's count them. 2, 4, 6, 8, 10. So we have 10 electrons in bonding. How about anti-bonding? So let's count for anti-bonding. 2, 4, 5. So we have 5 electrons in anti-bonding. Okay. Now we calculate the bond order. It's going to be 10 minus 5 over 2, which equals 5 over 2, or 2.5. Okay. So what does this mean? All right. So we can make a few points here. So let's write, so the strength of the covalent bond in NO has been shown so here's a little tidbit. It has been shown by experiment to be significantly stronger than the typical NO double bond. So this makes sense, right? Because if we look at the bond order, it's 2.5. So a bond order 2.5 is between a double bond and a single bond. So that kind of verifies that it's stronger than a typical double bond, and that's because it's 2.5. So actually the molecular orbital model is a little bit better in this case, because although the NO bond in NO in our Lewis structure suggests 2, by experiment, it actually suggests it's a little bit stronger than that. So 2.5 is the better prediction of bond order. Okay? So we can say this is in agreement I actually gave myself more room with the predictions. Of, molecular orbital theory. For the molecule. Okay. So the strength of the bond in NO. So some implications we can get from this is that the strength of the bond might explain why why this compound is stable despite the presence of an unpaired electron. So usually unpaired electrons are not very stable, and they tend to react with something to get an extra electron, but the bond order suggests that this bond is so stable that that lone pair that we drew up here for the Lewis structure is stabilized by the high bond order. So it's stable despite not having an octet for one of the atoms. And that might be due because of yeah, so it's really hard to say. So maybe it's interacting with the lone pair here, because we can't write another bond physically in the molecule because that would violate the octet rule. So maybe it's interacting with one of the lone pairs and stabilizing the molecule that way, even though it doesn't have an octet. So we can get some important implications from molecular orbital theory. So sometimes it trumps our predictions from valence bond theory. So these two theories here, they have to coexist to be able to explain something the other model can't. So that's the importance of MO theory. Okay, so that's it for chapter 10. I'm going to be posting some practice problems for 9 and 10. So students will have a chance to go over those. But that's it for this lecture. I'll end it here. So, and next week we will go into chapter 11, which is starting to talk about intermolecular forces between solids and liquids and gases. Okay. So I'll see everyone in the next one. See ya.